Hi everyone, welcome to my YouTube channel Erudispace. I am Dr. Mohanty, and before taking the lecture, wish you happy Holi. I expect that you will enjoy this day like all other holies. Today we'll discuss the steady flow energy equation. So before discussing the steady flow energy equation, I will give you the concept about the control volume. Then what are the basic assumptions made in steady flow energy equation. Then we will derive the equation for steady flow energy equation. And then we'll apply the steady flow energy equation for different components where flow actually takes place. So before discussing the steady flow energy equation, let me tell you what is a control volume. Control volume is similar to a closed system, but that is applied particularly when the flow of the working substance takes place. You have components like boiler, condenser, compressor, turbine, evaporator, number of components where there is a continuous flow of fluid. And for analysis of such cases, the control volume concept is introduced. In control volume, there is a continuous flow of mass taking place to the system or from the system to the outside or the surroundings. And as far as the viewer is concerned, his attention is focused on that particular fixed volume. Although the fluids continue to move, but as far as the focus of the viewer is concerned, that is focused on a particular volume, what we call your control volume. All of us know that according to the first law of thermodynamics, law of conservation of energy will hold good. And already we have discussed that the amount of heat that is supplied is equal to the change in energy plus the external work done. This equation will also hold good when it comes to steady flow energy equation, but will analyze each component of the energy that is coming out and that is leaving. But steady flow energy equation is also another form of law of conservation of energy, according to which energy can neither be created nor be destroyed. It can only be converted from one form to another. So for that, let us assume a control volume . This is a control volume. So it can be anything. It may be a boiler, it may be a turbine, it may be a condenser, it may be a compressor. So here, certain amount of fluid is actually entering and the same fluid is also leaving the system. And this is Z1 from the data. This is at Z2 from the data. The pressure and the specific volume are P1, V1. The velocity with which the fluid is entering is your capital V1. The internal energy, specific internal energy, because we are considering the unit mass of working substance. You can consider M mass also. It won't make any difference. Only thing that you have to multiply this. Then you have P2, V2, small v2. This is your pressure at the outlet, and this is the specific volume at the outlet. As far as the velocity is concerned, it is V2 here, and the specific internal energy is U2. And the amount of heat energy that is supplied is Q12 and amount of work output that we are getting is W1. If you want to note down also, you can note down your Z1 is the height, above datum, at entry point your P1 is the pressure of the working substance at entry, small v1 is the specific volume at entry, capital V1 is the velocity at entry, then small u1 is the specific internal energy at entry. Q12 is heat supplied and W12 is work done. Now I don't think that there is any doubt about what we have chosen, and Z2, P2, small v2, capital V2, small u2, these are the corresponding values at the exit point. And some of the authors, they do take this V1 at C1, which I have not taken, but that is specifically done to avoid confusion between small v and capital V, because small v represents the specific volume, whereas capital V actually represents the velocity. And if you inadvertently write small v for capital V or vice versa, then the entire analysis would be erroneous. So now what we'll do, we'll consider the law of conservation of energy, we'll consider the energy at the entry as well as the energy at the exit. If Q12 is the heat that is supplied, this is Q12 plus the internal energy at the entry, specific internal energy, small u1, plus we have to consider the flow work or the flow energy, that is the work done in pushing the working substance into the control volume, that is P1 V1, and obviously this is analogous to your displacement work when you are considering a closed system, plus this is V1 square by 2, that is your specific kinetic energy, plus ZZ1, that is specific potential energy, this is at the entry, and the exit you get U2, that is specific internal energy at exit, specific flow energy, that is the work done in pushing the working substance out of the control volume, plus capital V2 square by 2 plus ZZ2 plus W12. So this is nothing but your steady flow energy equation, and if you are considering m mass of the working substance, then you have to multiply m on both left hand as well as the right hand side. And particularly when you are considering a steady flow, means the mass flow rate remains constant, the energy interactions do remain constant. That means you have the heat as well as work remaining same with time, and there is no chemical reaction taking place when the flow is taking place. So these are the conventions that you have to follow, and this actually represents your steady flow energy equation. If you carefully analyze everything, you can say that Q12 is equal to U1, sorry, this is U2 minus U1 plus P2 V2 minus E1 V1 plus V2 square by 2 minus V1 square by 2 plus Z2 minus ZZ1 plus W1. Now, what are these things? All these are different forms of energy differences. This is nothing but your du, that is change in internal energy. Then this is your change in flow energy, change in kinetic energy, change in potential energy. So this is also can be represented in the same way. Q12 is equal to del E plus W12. That is something that we have discussed while discussing the first law of thermodynamics for a closed system undergoing a change of state. The same thing is happening in this case. But usually what we do represent the sum of the flow work as well as internal energy as enthalpy, because all of us know that enthalpy is the sum of internal energy plus pressure volume product. That is nothing but your flow work or flow energy. So this can be represented in this way: Q12 plus H1 plus V1 square by 2 plus ZZ1 is equal to your H2. This represents your H2 plus V2 square by 2 plus ZZ2 plus W12. And you need to remember that here we are considering the unit mass of substance. If you consider m kg mass, then you have to multiply m with this, because don't get confused that this is being represented by b square by 2, because here we are considering unit mass of the substance. This is ZZ1. Usually when we represent the kinetic energy or the potential energy, the usual terms are mv square and mgz. But here, as we are considering specific kinetic energy and specific potential energy, we are using these terms. So this you can say as an expression for the steady flow energy equation, and both represent the same thing here, only the H1 is substituting the internal energy plus the flow energy. So now what we'll do, we'll apply this steady flow energy equation for different components like your boiler, your condenser, your turbine, your evaporator, and the different components, and we'll see that what is actually happening to the steady flow energy equation. In all the cases I have told you that this equation Q12 plus enthalpy plus, this is your, of course, your specific enthalpy, then your specific kinetic energy, so this equation will hold good. Let us first consider a boiler. So in a boiler what we do, suppose this is a boiler. and this is the furnace. Here water is entering and you are getting steam. Water entering the boiler, and you can consider this to be a control volume. This is your boiler, this is your furnace, and you are getting steam. So here actually what is happening to the steady flow energy equation? Here actually heat is being added. And the enthalpy at the entry condition is H1, and as far as the kinetic energy is concerned, that is negligibly small, and if it is at the same level, you can also eliminate the potential energy, because the potential energy at one end will actually balance the potential energy at the other end, that is equal to H2. No work is done in boiler, so this will become 0. We have considered this to be 0, this to be 0, and this potential energy at left hand side will cancel out the potential energy at the right hand side. Now you get Q12 as H2 minus H1. So this is happening to the steady flow energy equation when it comes to the boiler. Then we'll take the case of a condenser. In condenser, what happens? In condenser actually it liberates heat to the surroundings, and the process that is taking place is reverse to that what is happening in case of your boiler. And another thing that you need to remember, that the basic sign conventions of energy interaction will be exactly same. There will be no change in that, whether you are considering a closed system or a control flow. Heat transfer to the system will be taken as positive, heat transfer from the system will be taken as negative, work done by the system will be taken as positive, and work done upon the system will be taken as negative. So let us consider a condenser. So here, what is actually happening, that it is liberating heat to the surrounding, and when it is liberating heat to the surrounding, what is actually happening to the energy equation, that will analyze in case of condenser. So when it is releasing heat, so this Q12 will be given a negative sign, and the enthalpy is H1. As far as the kinetic energy is concerned, kinetic energy both at the entry and exit will be negligibly small, and as it is at the same level, the potential energy component can also be eliminated. So that is equal to your H2. Now okay, this becomes the energy equation when it comes to your condenser. In case of boiler, it is Q12 equal to H2 minus H1, whereas in this case it is Q12 is equal to H1 minus H2. So now actually we will discuss what is happening in case of turbine and compressor. First let us consider the turbine, and here the working substance is entering, and here the working substance after being expanded, the working substance. working substance coming out. So in this case actually what is happening, that if you insulate the turbine, then the heat interaction is 0. Now what is happening to the energy equation? It is equal to H1 is equal to H2 plus W1. Because in this case the kinetic energy component can be neglected. If it is at the same level, the potential energy on the left hand side will actually balance the potential energy on the right hand side, and this will be the equation. And W12 is equal to H1 minus H2, that is the difference in enthalpy. Next we will consider what is happening in case of a compression. Compressor actually compresses the working substance on consuming the work. In compression, work is actually done upon the system. So what is happening in case of a compressor? Let us see. Here again the working substance is entering and it is leaving substance in, and this is your working substance out. So when we are considering the steady flow energy equation for a compression, no heat interaction is taking place, so that component is 0. Now you have H1 is equal to H2 minus W12. Why negative sign is given? Because work is done upon the system in compressing the working substance, and the basic sign convention is to be followed. And as far as the other things are concerned, the kinetic energy is negligibly small. If both the ends are at same level, the potential energy can be eliminated. So in this case, W12 is equal to H2 minus H1. So when you are considering the compressor and the turbine, you find that this is W12 is equal to H2 minus H1 when it comes to your compression, and when it comes to turbine, W12 is equal to H1 minus H2. This is due to the reason that in case of compression, work is done upon the system, whereas in case of turbine, work is obtained from the system. Then we will discuss what is happening in case of a nozzle. Nozzle is actually a smoothly varying section where the kinetic energy is increased, and the nozzle may be a convergent type, it may be a divergent type, or it may be a convergent divergent type. Here working substance in, working substance out. In this case, no heat is supplied, no work is obtained or done upon the system. So in this case, the energy equation becomes H1 plus V1 square by 2 is equal to H2 plus V2 square by 2, because no heat is supplied, no work is obtained. The potential energy on left hand side actually balances the potential energy on the right hand side, and now H1 plus V1 square by 2 is equal to H2 plus V2 square by 2. You can say that V2 square by 2 is equal to H1 minus h2 plus v1 square by 2. Usually what is observed that the velocity at the entry is negligibly small, so it can be neglected. So if you neglect that, you get v2 square by 2 is equal to 2 into h1 minus h2, not 2, sorry, this is h1 minus h2. So this implies v2 square is equal to 2h1 minus h2, and then v2 is equal to square root of 2h1 minus h2. Now we have applied it to different components like your condenser, your boiler, your turbine, your compression, your nozzle. It can also be applied to other components like your diffuser, your evaporator. Once you know what is happening and what are the energy interactions, which energy interaction is zero or neglected, you can easily derive the expression for any device where flow is taking place. So I sincerely believe that today's lecture would be extremely useful for all of you in understanding the concept of steady flow energy equation, what is its utility and its applications. If you have any doubt, please do put questions so that I will try to answer. Thank you very much for watching this video. Hope to see you soon for another lecture on my YouTube channel Erudispace.